Welcome to the KY Safe e-training webinar for machine guarding. My name is Zach Zimmerman, and I'm a safety consultant with KY Safe. Please pause the presentation and read this disclaimer. When you are ready, press play to continue. This training will cover OSHA's 1910 Subpart O over machinery and machine guarding. The objectives for this webinar are to cover the OSHA requirements for machine guarding, understand types of machine guarding and their purposes, recognize common hazards and solutions. Year after year, machine guarding standards are one of the most commonly issued citations. Unguarded machinery is especially dangerous, and approximately 18,000 injuries and over 800 deaths will occur each year to workers who operate machinery. Amputations are among the most severe and crippling injuries that can occur in the workplace and often result in permanent disability. Machinery accidents can occur when workers reach inside to clear blocked or jammed equipment, when maintenance is performed on equipment without following proper lockout tagout procedures, when unauthorized persons attempt to perform maintenance or use machinery, when machine guards are missing or not properly installed, when workers do not use close proximity devices like push sticks when operating machinery. Amputations are widespread and involve a variety of activities and equipment. Each year, thousands of workers lose fingers, hands, feet, and other body parts, mostly through compression, crushing, or getting them caught between or struck by objects. Most amputations involve fingertips. An injury is considered an amputation if there is the traumatic loss of a limb or other body part. Most amputations occur in the following scenarios: operating unguarded or inadequately guarded machinery, material handling operations including the use of forklifts, compactors, and hand tools, and during activities involving stationary machines. This includes setup, threading, preparing or adjusting machinery, cleaning, lubricating, maintenance, and when clearing jams. Caught-in injuries occur when a person is pulled into or caught in equipment. This also includes strangulation as a result of clothing caught in running machinery. Crush-by injuries occur when a body part is compressed by excessive force or pressure. Struck-by injuries are caused by an impact between a person and an object or piece of equipment. An example of this could include something being ejected from a machine back into an operator. The key factor in making a determination between a caught event and a struck event is whether the impact of the object alone caused the injury. When the impact alone creates the injury, the event should be recorded as struck. When the injury is created as a result of crushing injuries between objects, the event should be recorded as caught in. The fundamental machine areas that need to be known are point of operation, power transmission device, and operating controls. The point of operation is where work is performed on the material. This includes cutting, shaping, boring, or forming of stock. The power transmission device transmits energy to the part of the machine performing the work. Operator controls can either be mechanical or electrical. This is the area of the machine that makes it possible for the operator to cut off the power from the machine without leaving his position at the point of operation. The power transmission apparatus is all components of the mechanical system which transmit energy to the part of the machine performing the work. These components include flywheels, pulleys, belts, connecting rods, couplings, cams, spindles, chains, cranks, and gears. The actions or motions that machines perform can present different hazards to workers. A motion is defined as how the machine part is moving, and action is the operation that the machine part is performing. These can include the movement of rotating members, reciprocating arms, moving belts, meshing gears, cutting teeth, and any parts that impact or shear. These different types of hazardous mechanical motions and actions occur in varying combinations in nearly all machines, and recognizing them is the first step toward protecting workers from the danger they present. The basic types of hazardous mechanical motions and actions are, for motions, rotation, in-running nib points, reciprocating, and transversing. For actions, cutting, punching, shearing, bending. These will be illustrated on the next few slides. Here's an example of rotating and in-running nip point motions. Here's an example of reciprocating and transversing motions. Here are cutting and punching actions. And here we see shearing and bending actions. To be effective, machine guarding safeguards must meet these minimum requirements. The guard should prevent contact between the hazard and a worker. The guard should be firmly secured in place. The guard should create no new hazards or interference on the machine, and it should still allow for safe lubrication of the machinery. Guards used to provide a barrier between the worker and dangerous equipment are the most common method of safeguarding, but devices can be used as well. These are controls or attachments like light curtains and pullbacks that prevent inadvertent access by employees to hazardous machine areas, or interrupt power to the machine to cut off the hazardous movement. Machines can also be guarded by location or distance. This involves positioning the dangerous part of a machine in an area that is not accessible to workers, so it no longer presents a hazard. Two most common type of guards are fixed guarding and adjustable guarding. Fixed guarding are guards that are permanently fixed in place and is not dependent on moving parts to function. This guard is usually the preferred type because of its simplicity. Adjustable guards are guards which can be adjusted to accommodate various sizes of stock. Because these can be adjusted and changed, they can be more dangerous than fixed guards if they are not set up properly each time. The point of operation on a machine is where work is actually being performed upon the material being processed. Any machine with a point of operation that exposes an employee to injury must be guarded. A few examples of machines that require point of operation guarding are guillotine cutters, shears, alligator shears, power presses, milling machines, power saws, jointers, portable power tools, farming rolls, and calendars. Fans that are less than 7 feet above the floor or working level must be guarded. Fan blade guards cannot have openings that are larger than half an inch. Abrasive wheel machinery like a bench grinder requires a variety of guards. The tongue guard on the top part of the wheel should be adjustable and never have a gap greater than 1/4 an inch between it and the wheel. The work rest should have a maximum opening of 1/8 an inch and be adjusted as the wheel wears down. The spindle end, nut, and flange projections on the grinder should also be covered by a guard. Revolving barrels, containers, and drums must be guarded by an enclosure interlocked with the drive mechanism. So the barrel, drum, or container cannot revolve unless the guard is in place. The guard openings can be no larger than half an inch. Power transmission apparatuses such as shafting, flywheels, pulleys, belts, or chain drives that are less than 7 feet from the floor or working surface must be guarded. The machinery most frequently involved in amputations, one of the most devastating of workplace injuries, are shown on this slide. These machines should be guarded, especially at the point of operation, to reduce the risk of amputation. All guards should meet these minimum requirements. The safeguard must prevent hands, arms, and any other part of a worker's body from making contact with dangerous moving parts. A good safeguarding system eliminates the possibility of the operator or another worker placing parts of their body near hazardous moving parts. Workers should not be able to easily remove or tamper with the safeguard, because a safeguard that can easily be tampered with is no safeguard at all. Guards and safety devices should be made of durable material that will withstand the conditions of normal use. They must firmly be secured to the machine. The safeguard should ensure that no objects can fall into moving parts. A small tool which is dropped into a cycling machine could easily become a projectile that could strike and injure someone. A safeguard defeats its own purpose if it creates a hazard of its own, such as a shear point, a jagged edge, or an unfinished surface, which can cause a laceration. The edges of guards, for instance, should be rolled or bolted in such a way that they eliminate sharp edges. Any safeguard which impedes a worker from performing the job quickly and comfortably might soon be overridden or disregarded. Proper safeguarding can actually enhance efficiency as it can relieve the worker's apprehensions about injury. If possible, one should be able to lubricate the machine without removing the safeguards. Locating oil reservoirs outside the guard with a line leading to the lubrication point will reduce the need for the operator or maintenance worker to enter the hazardous area. The two primary methods used to safeguard machines, guards and safeguarding devices. Guards provide physical barriers that prevent access to danger areas. Safeguarding devices either prevent or detect operator contact with the point of operation or stop potentially hazardous machine motion if any part of an individual's body is within the hazardous portion of the machine. Both types of safeguards need to be properly designed, constructed, installed, used, and maintained in good operating condition to ensure employee protection. Both guards and devices should be properly designed, constructed, and installed. They should also be maintained so that they are always used in good operating condition. Guards usually are preferable to other control methods because they are physical barriers that enclose dangerous machine parts and prevent employee contact with them. To be effective, guards must be strong and fastened by any secure method that prevents the guard from being inadvertently dislodged or removed. Guards typically are designed with screws, bolts, and lock fasteners, and usually a tool is necessary to unfasten and remove them. Generally, guards are designed not to obstruct the operator's view or to prevent employees from doing a job. Guards must not create additional hazards such as pinch points or shear points between guards and other machine parts. Guard openings should be small enough to prevent employees from accessing danger areas. Guards can be fixed to the machinery, interlocked so that the guard must be in place in the machine to run, adjustable or self-adjusting to fit a variety of stock. As the name implies, a fixed guard is a permanent part of the machine. It is not dependent upon moving parts to function. It may be constructed of sheet metal, screen, wire cloth, bars, plastic, or any other material that is substantial enough to withstand whatever impact it may receive and to endure prolonged use. This guard is usually preferable to all other types because of its relative simplicity. The advantages of fixed guards are they can be constructed to suit many specific applications. In-plant construction is often possible, can provide maximum protection, usually requires minimum maintenance, can be suitable to high production repetitive operations. The potential limitations of fixed guards are they may interfere with visibility, they can be limited to specific operations, machine adjustment and repair often require its removal, thereby necessitating other means of protection for maintenance personnel. When interlock guards are opened or removed, the power to the machine automatically shuts off or disengages. The moving parts of the machine are stopped, and the machine cannot cycle or be started until the guard is back in place. An interlock guard may use electrical, mechanical, hydraulic, or pneumatic power. Replacing the guard should not automatically restart the machine. To be effective, all removable guards should be interlocked to prevent occupational hazards. Advantages of these guards are they can provide maximum protection and they allow access to the machine for removing jams without time-consuming removal of fixed guards. However, the guards require adjustment and maintenance, and they may be easy to disengage or bypass. Adjustable guards are useful because they can allow for a variety of production operations. They can be adjusted so that various sizes of stock can be worked on by the same machine. They can be constructed to suit many specific applications, but they may require frequent maintenance or adjustment. The guard may be made ineffective by the operator, and if they are not adjusted correctly, operators' hands may enter the danger area, or protection may not be complete at all times. For self-adjusting guards, the barrier is determined by the movement of the stock. As the operator moves the stock into the danger area, the guard is pushed away, providing an opening which is only large enough to admit the stock. After the stock is removed, the guard returns to the rest position. The guard protects the operator by placing a barrier between the danger area and the operator. However, these may not always provide maximum protection and may require frequent maintenance and adjustment. Safeguarding devices include controls or attachments that prevent employees from coming into contact with the hazardous areas of machinery. Probe detection or safety edge devices halt the machine's action when certain areas of a machine are touched. Devices like light curtains and pressure sensing pads require an employee to be in a certain area for the machine to function. Pullback devices function by physically removing an employee's hands from the machine when it cycles. Secondary safeguarding methods are acceptable only when the guards or safeguarding devices cannot be installed due to reasons of infeasibility. Secondary safeguarding methods may supplement these primary control measures. However, these secondary safeguarding methods must not be used in place of primary safeguarding methods. These methods aim to design the process of the work to reduce the hazard by changing distances, openings, and how the work is done. This is the hierarchy of controls. This illustrates the most effective steps to take in order to control a hazard. The first step is elimination. Can the hazard be removed from the workplace? Next, substitution. Can the hazard be replaced with something less hazardous? Then engineering controls. Can we isolate people from the hazard? This is where machine guarding falls. Next, administrative controls. Can we change how people work to reduce their exposure to the hazard? Finally, PPE, the least effective step. It protects the worker with personal protective equipment. This chart is an example of how to work through the hierarchy of controls with regards to machine guarding. First, can we eliminate or substitute out the machinery altogether? This is usually not possible if the equipment is required for production. So next, we look to control the hazard through engineering means. Consider which type of guard will be most effective for the equipment. Can other safeguarding devices or designs be effective at controlling the hazard? Next, administrative controls. What safe work practices should employees follow in order to safely use this equipment? And finally, PPE. What personal protective equipment could provide additional protection to employees? This may include safety glasses, face shields, gloves, and more. It is recommended that employers develop a machine guarding program to effectively protect their employees from the hazards associated with this equipment. This program may include things such as conducting inspections, determining the point of operations and dangerous motions and actions of equipment, and training employees on machine guarding. You can scan this QR code to view OSHA's recommended practices for safety and health programs. Conduct a hazard assessment in your workplace. Inspect the workplace for potential hazards involving dangerous machinery. Identify hazardous actions and motions of machinery that require guarding. Install guards to protect employees from equipment. Have employees that use guarded equipment conduct pre-use inspections before they use the equipment each day. These inspections may include a visual check, an operational test, checking for modifications or bypasses to the guards, inspecting for loose parts, ensuring guards do not make equipment inaccessible or more dangerous to use. Equipment should continually be evaluated and monitored to ensure it remains free from hazards. Schedule periodic reviews to ensure that guards are still effective. Check guards for signs of wear, corrosion, or damage. Document the condition of guards and any concerns. Review past incidents involving machinery. Train employees on how to properly use equipment with guards in place. Train employees to recognize damaged or missing guards. Encourage employees to report any guarding issues and develop an effective reporting system that promptly responds to these reports. A quick check to ensure that guards are effective is to consider the auto principle when evaluating guards. Guards should prevent anyone from reaching around, under, through, or over the guard to contact a hazard. To wrap up this webinar, keep in mind the auto principle when evaluating the effectiveness of guards. Ensure that the point of operation and dangerous machine actions and motions are guarded. And finally, develop a plan or program to address machine guarding in the workplace. For more free online learning opportunities and to learn more about our services, please visit our website, kysafe.ky.gov. Thank you for watching this presentation.